Hey guys, Miss McCorn here. We're going to continue with Unit 6 Thermodynamics. We're going to look at 6.4 and 6.6 Heat Capacity, Calorimetry, and Intro to Enthalpy of Reactions. So your learning targets are listed right here. You can go out your handy dandy notebook, start taking some notes, and put these into your own words. Make sure that we have already looked at this Q equals mc delta T. It's really important, and we're going to start to apply it more and more throughout this unit. So go ahead and pause the video and get those notes. The first law of thermodynamics is super important, and we've really already talked about it. It's like the law of conservation of energy. Energy cannot be created or destroyed, it can only be transferred. So the internal energy of a system, we can actually transfer that energy into or out of the system in the form of heat or work, but we can't create or destroy any of that energy. So we looked at that a lot on Friday, where we saw that heat transfer or that work transfer, but none of that energy was created or destroyed. Either the heat or work went into the surroundings, or it came from the surroundings into the system. Okay, so one of our most important things in this unit to really truly understand is specific heat capacity. Okay, we look at that in our Q equation as C. That's the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Kelvin. And this is going to be different depending on the compound or molecule or atom that you have. So you might have iron, which has a very low specific heat. It takes a whole lot of heat to raise the temperature of iron by 1 Kelvin. Whereas for water, it doesn't take it takes a lot of heat to increase the value of water, but not so much for iron. That is because iron is a good conductor of heat. We know that iron and all metals transfer the electrons. That electron C model, they're very free, and the electrons can transfer energy from one to another, and we can look back at that electron C model to understand that a little bit better. But when we look at that demo that we did on Friday, it's really interesting to know that it didn't take very much heat to get that iron to get really hot. But the water, when we dropped that really hot iron into the water, it came down very quickly. The temperature of the iron came down very quickly, but the water didn't heat up much at all. So I want you to think back to that when you think of specific heat. So remember when I introduced this equation here, this Q equals mc delta T, we kind of just glazed over it a little bit, but really want to point out that the material with the higher specific heat capacity, so when the C is higher, that means that it's going to experience a smaller increase in temperature. So the higher this is, the lower this has to be in order for the Q to kind of remain constant. I hope that makes a little bit of sense. You can go ahead and take just a minute to pause the video here and get a really good handle on what each of these, not constants, I apologize, what each of these variables in this equation means. This is super important. Now, calorimetry is the way that we can use to measure heat transfer, and we are going to do this with our lab on Tuesday. Since we can't measure heat directly, we can measure temperature. We're actually going to use a calorimeter to measure the temperature before and after a reaction, and we're going to be able to use the data to calculate heat transfer. So I think you guys are going to be really interested in that lab that we do tomorrow. Now, this is kind of what it's going to look like. What we will use on the outside here is we're going to use like 2 styrofoam cups here in order to kind of insulate our water. And we are going to have a stir and a thermometer, and that is going to measure it. Now, what I want you to remember is that our solution is going to include our water, and that's going to be our surroundings. Okay, our surroundings are going to include our water, and then the system is going to be all the other molecules in here. So our surroundings are going to include the water. So when they may use the word solution, the mass of the solution. So I shouldn't say solution here. I should say the water is the surroundings, and the solution, I'm so sorry about this stupid pen again. The solution is going to be the system. That's going to be all these little colored molecules in here. That's our system. And then this little mess over here. How about we write it again? Okay. The water really would be our surroundings. Y'all are going to have to do a little research for me and figure out if I can get a pen that's actually not going to do this, because this is foolishness. So to do our experiment, what we're going to do is we are going to get the mass of the solution in the calorimeter. So you're going to actually add a mass of something into this, and you're going to know what the mass is, of course. And then we're going to get the initial temperature of the solution and the final temperature. Okay, and so that's going to be our delta T. And then our Q, we're going to measure. We're going to use our Q equals MC delta T. And we're going to use our C is going to be the specific heat of water, mostly because when we put all of this into water, water is generally going to have more volume. So the volume of the whatever the substance is that we put in there is going to kind of be negligible. It's not going to matter quite as much. So we'll use our C as our specific heat of water. We'll know the mass that we put in there. We'll know our delta T because we'll measure that, and we'll be able to calculate Q. And we'll do that in the lab tomorrow. Okay, so this is kind of telling you exactly what I just told you, but this is in a much nicer format. So go ahead and pause the video here, write this down. That way, or maybe, take a little snip of it, put it in your notes. That way you'll be totally prepared for that lab tomorrow. So when we do that lab, so when you're going in and you are doing your pre-lab questions this evening, when we're doing that lab tomorrow, when you're doing your post-lab questions, the reactants of the products are the system, and the water is going to be the surroundings. Okay? The heat lost or gained by the solution is going to be the same as we consider the heat lost or gained by the reaction. That's going to be the whole thing. Okay? So go ahead and pause the video here. If you need to take any notes on it, make sure you're taking notes. We are going to use Q of the reaction. This is how we'll write it. Is going to be equal to negative MC delta T. The reason we're going to use the negative here is because we are actually measuring the temperature change of the water. So since we're measuring the temperature change of the water, we're measuring the temperature change of the surroundings. So we actually have to change the sign, because we want to actually have our answer be the temperature change of the surroundings. We want our Q of our solution, which means we want the Q of this. So to get the Q of the system, we have to change the sign, because whatever is going into here is going out of here, or vice versa. So they'll be opposites. So remember, when the system, whatever's going into the system will be coming out of the surroundings. Whatever's going out of the system will be going into the surroundings. So they'll have the same exact value with different signs. So some of the things on this slide may seem a little confusing unless we do a few examples in class, which we will do in a few minutes. But what we want to focus on here is just enthalpy change, which is delta H of a reaction. It's the amount of heat energy that is released or absorbed by a chemical reaction. There are 4 different ways we can do that. This here we're going to do in 6.9, Hess's law. Enthalpies of formation, average bond enthalpies, and of course what we're doing with calorimetry experiments we are going to be doing in the lab. So when we talk about the difference between the Q, or the heat of the reaction, and the delta H, or the change in enthalpy of the reaction, it's a little bit different. So the Q, or the change in the heat of the reaction, that's the heat loss or gain in an experiment. Okay, so we're talking experimentally here with a calorimeter. Whereas the delta H, we're actually talking about the balanced chemical equation. So when we talk about the Q of the reaction, we're actually using numbers that we do with measurements. Here, we're probably going to be talking about some molar values. So generally, we're going to put grams in here. We're going to put moles in here. That's where your big difference will be. Molar heat capacity, very simply, is C with the M there. That means instead of using grams, it's how much heat requires to increase the temperature of 1 mole of a substance by 1 Kelvin. This, of course, is in the same ratio as it is for regular old specific heat, large for water, small for iron. I want you to pause the video here just so you can get an idea of how to get molar heat. We will do some practice problems in class. Okay guys, so we're about to start class now. What I want you to do is just make sure your notes are all ready, and we are going to do lots and lots of practice today. All right, let's get started.